How are you guys? Yeah. Good morning, good evening, good afternoon, depending wherever you are seeing on the globe. Today we are just going to do our practical 3, titration practical 3, and we are proceeding with our series. So today, the procedure is just clearly on the board. By the way, I'm Charles Alena. I'm just trying to introduce to you to practical 3, titration practical 3. You are provided with the solution E made by dissolving 5.6 grams of potassium hydroxide pellets in 250 cubic centimeters water, and the solution diluted to make up to 500 cubic centimeter solution. Then solution F, the E4, this sulfuric acid and phenolphthalein indicator are also provided. You are also required to determine the concentration of sulfuric acid in moles per liter. This is the procedure. We are supposed to fill the burette with the sulfuric acid using the pipette filler and pipette 25 cubic centimeters of the potassium hydroxide solution into a clean conical flask and add 2 to 3 drops of phenolphthalein indicator. Titrate potassium hydroxide solution with sulfuric acid solution and record the results in the table below. So here. So now we will just assume that we have done that titration practical, and we have found the average volume as follows. Because the average volumes are supposed to be tabulated in the table below, above. So, for example, let us assume that our initial burette reading, we filled the burette up to the 0 mark, and it was 0.0. Now we have titrated, and then the solution has changed to 20.0. So we come here, we write our final burette reading 20.0. Now, after we have done that, we have stopped at the mark 20. Now, we are supposed also to do the second titration. So, we shall titrate. So, the 20.0 now becomes our initial burette reading for the second titration, right? So, now, we will come and write here 20.0. Then, we titrate, maybe now, the final volume, the final volume for burette reading that will change, maybe it turned at, let us assume it is 40.10. Then from there, we will now refill back the burette. Let us now assume that we have refilled the burette up to because it is at 40, now we have refilled the burette up to 10. So we shall come and write here 10.0. So, after we have refilled the burette to 10.0, maybe we have titrated and then it has changed, we assume at 30.0, right? 30.0. So, when we will start now taking the volume of the acid used in each column, we shall subtract the final burette reading from the initial to get what? 20.0. And then, here we shall get what? 40.1 minus 20, we shall get what? 19.9, right? 20.1. Yes, you can also talk. It is allowed. 20.1. 20.1, yes. Remember, this is 40.1. Yes. And this is 20.0. So, we will get what? 20.1. 20.1, right? Yes. Like that. Yes. Are we really supposed to get that one for it? Yes. Let us now assume it is 20.1 here, so that we can get also 20, right? Yes. Like that, right? Yes. So now we will go even to the third column. We subtract final burette reading from initial, right? Yes. So we shall get what? 20.0. So we have been asked in our questions, determine the average volume of the solution for F4 used. So solution Solution F4 used, which is sulfuric acid. So we shall just say, determine the average volume of the acid used. So we shall just write average volume of acid used is equals to, let me economize some space here, is equals to first titer plus second titer volume plus third titer volume. And then everything is supposed to be what? In cubic centimeters. So in an exam, you are supposed also to write this because it is mass. I have a mark, eh? So we shall come to substitute this. Eh? So we shall come here and make sure your equal signs are supposed to be on the straight line, right? So we shall come here and let's say 20.0 plus 20.0 plus 20.0, right? Let us assume that we got the accurate results like that, right? So everything is supposed to be what? In cubic centimeters, right? So here we are going to get what? 60 divided by 3, right? 60 divided by 3, which is equivalent to 20.0 cubic centimeters. Remember to maintain this one decimal point because it's very, very important in as far as titration is concerned. And also you are supposed to tabulate your results. It's supposed to be in decimal point. One decimal point. If you have maintained one decimal point, maintain all throughout your table. Sounds up? Yes. Now, we go to the second question. We have been told to determine the number of moles of potassium hydroxide used. So B, determine the number of moles of potassium hydroxide that was used, if I'm not wrong. So we have been given here relative atomic mass of potassium is 39, oxygen is 16, and then hydrogen is what? Is equals to 1. So in this case, the number of moles of hydrogen the number of moles of potassium hydroxide that were used, we are going to approach it this way. We have been told 5.6 of these were dissolved and made up to 500, isn't it? Yes. So we are going to ask ourselves, 5.6 grams were dissolved in what? In 500 cubic centimeters, right? So what about in 1,000, right? 1,000 cubic centimeters. So in this case, we are going to cross multiply this over that, right? Yes. So we are going to have 5.6 times 1,000 cubic centimeters. Then we divide by what? 500, right? So all these, they are what? All these are grams per liter. Because we are trying to get, these ones are the number of grams that were dissolved in 500. What about for 1,000, right? So these are X. So we are trying to get the number of grams that were dissolved in 1,000 first. So we go back to our calculator here. So we get 5.6 times 1,000 divided by what? 500, right? The answer is 11.2 grams. So we come here, we write 11.2 grams per liter. Remember, we have only found out the number of grams. We have not determined the number of moles yet. We are still just on the way, right? So you are supposed to follow Kimberly so that you don't get lost. So in the long run, we must first get the number of the relative formula mass of potassium hydroxide. So we are going to calculate it like this. Potassium hydroxide. Relative atomic mass of potassium is what? We have been given somewhere here. 39, right? Yes. So 39 times 1, right? You get 39, right? And then oxygen is 16 times 1, right? Yes. We get 16, right? So, and then hydrogen is 1 times 1, right? You get? So totally is how many grams? 56 grams, right? 56 grams. 56 grams. So after we have gotten that 56 grams, we are supposed to we are now going to write the molarity. What is the molarity? Molarity is equals to mass in grams per liter divided by what? RFF, right? So it's going to give you what? Mass in grams per liter, we found it to be 11.2, right? 11.2. I am supposed also to economize space. And then the RFM, we have found it to be 56, right?
Yes.
So, 56. So we go back to our calculator. Very fast. You are not even supposed to waste a lot of time here. Divide by it. Go ahead. Wait for a minute. Divide by 56. 0.2, right? So it's going to be 0.2. 0.2 m. Okay. This is our molarity of this. Of potassium hydroxide. So now in the long run, we are going to ask ourselves, if 1,000 cubic centimeters is giving us what? 0.2 moles, right? Yeah. What about, remember, when we were pipetting, we were using 25 cubic centimeters, right? So we are going to ask ourselves, what about for 25 cubic centimeters? So it's going to be 25 times 0.2 divided by 1,000. Okay? These are the number of moles, right? So it's going to give us what? It's going to give us, if we divide very well, we are going to get this. 25 times 0.2 divided by 1,000 is equals to 0.0 what? 0.005, right? Moles. So we have answered that. Okay. So after that, now we are going to determine the number of moles of sulfuric acid used. So we are supposed also to economize space like that. So determine the number of moles of sulfuric acid used. Number C. Determine the number of moles of sulfuric acid that were what? That were used, right? Acid used. So in this case, we must write the chemical equation first. Sounds up? So we must make sure that we write the chemical equation so that it can be able to direct us on to get the accurate result. So we will come here and then say potassium hydroxide plus sulfuric acid. We get what? Potassium sulfide, right? Potassium sulfide plus what? Plus water. Isn't it? Sounds up? Yes. So we go back and write the status. Right? So this one is supposed to be, it is aqueous, and also this one is aqueous, right? This one is aqueous, and this one is a liquid, right? So, is our equation balanced? Potassium sulfate, it has a 2 here. Okay, so we are going to write 2 here so that our potassiums to balance. And then our oxygens, we have 2 oxygens plus this one. 2 oxygens plus this one is 6, isn't it? So on the reaction sides, we have 6 oxygens, right? And then on the product side, we have how many oxygens? 1, This one's at 4 plus this one's 6. Eh? So we add a 2 on the water. We have 2 molecules of water there, right? So how many hydrogens do we have? 2 hydrogens, right? And here 2 hydrogens, right? 4 on the reactant side, right? The product side, it is also giving 4 hydrogens, right? So our equation is balanced, right? So we need to ask ourselves, if we have such kind of an equation, potassium hydroxide plus sulfuric acid, it is giving us potassium sulfate plus 2 molecules of water. Then the mole ratio is 2:1. So you write here mole ratio is 2:1. Sawa. Simple potassium here. Sulfuric acid is here. Sawa. So these are the mole ratio. And remember, we have been asked to calculate how many, to determine the number of moles of sulfuric acid. So, and we know very well the number of moles of sulfuric acid of potassium hydroxide, they were 0.5, right? So if potassium hydroxide is equal to 0.005, and yet potassium hydroxide has got this. The mole ratio is 2. So it means now the number of moles of sulfuric acid is going to be kuna mtu anafloat up to there. Do you have somebody who is floating up to that point? We are dividing it by 2 because of the mole ratio. Yes. Are you really following? Yes. So this one, it is there. It's going to give us 1 times 0.005 divided by 2, right? So it's going to give us what? 0.005 moles, right? Of sulfuric acid. So 0.0025 moles. So the last question, we have been told to determine D. This is number A, B, C, and then D. Yes. We have been told to determine the concentration of sulfuric acid in moles per liter. Very simple. You just come here. You say if 20, this is our average volume. Where is it? Here. 20 can give us this. 0.0025 moles. What about 1,000? 1,000 cubic centimeters. You come here and say 1,000 times 0.0025 divided by 20. It's going to give us what? 1,000 times 0.0025 divided by 20. 0.125 M. I think that one has come to the end of our virtual practical class. Meet you next time, but remember to subscribe, to like, and also to share. Otherwise, thank you in advance. Bye-bye.